So this is the second class of crystal structure, part of solid state physics. Now the outline of this class is basically recapitulation of the first class, which I have read in the first class. Second, the direction in crystal. The third part is different indices which ultimately characterize the planes or the family of planes in the crystal system. And then I'm going to discuss the cubic system, different type of indices, how we can find out different kind of indices in cubic system, and then the same thing which we are going to adopt in case of hexagonal system, and the last part, which is the relation between the planes and the direction. So first, in my first class I have told you that the solid is made basically classified into crystalline and amorphous material. In case of crystalline material, there is periodic arrangement of atom in definite size. You have seen that left hand side it is silicon dioxide, which is a quartz crystal, and the right hand side it is the glass. This is amorphous silicon dioxide. So depending on the crystalline or the amorphous material, different properties of the same substance become different. In case of glass, there is random orientation or random arrangement of atom. There is no periodicity in at all, and in case of crystal, as there is periodic arrangement, this periodic arrangement of the crystalline solids described as the network of different points, which is called a space lattice. Now a space lattice I have defined in the first class, that is the identical that is the point or the point that is distributed in the space in the regular fashion, having identical surroundings. And you have already read that there are 14 types of 3D Bravais lattice in case of 7 crystal system, and we have characterized them by different lattice parameters A, B, C, and alpha, beta, gamma. So these are the 14 types of Bravais lattice: simple cubic, body centered cubic, face centered cubic, obviously simple tetragonal, body centered tetragonal. There is rhombohedral, hexagonal, and triclinic, and obviously now simple orthorhombic, body center orthorhombic, base center orthorhombic, face center orthorhombic, and obviously monoclinic and base centered monoclinic. Now these are some example of different crystal system with these compounds are basically crystallized in this kind of crystal system. Now the second portion after recapitulation, how could you find the coordinate of a point in the unit cell? So you have taken an unit cell, and particularly in first case you have to choose a coordinate system, definite coordinate system, which is chosen by me in here, as is x, y, z. This is the coordinate system, and this 3 coordinate system, the axis of this coordinate system must be coincide with 3 edges of the unit cell, and we have to define the 3 lattice vectors, that is ABC. Now you just take a particular direction. Say for example, the point which is located in this figure, that is basically located in a such place where it intercept along x-axis at a by 2, along y-axis in b by 2, and along z axis in c by 2. That is shown in the figure. So coordinate of that particular point with respect to origin must be half, 1/3 or half. But this representation of direction is probably problematic in case of crystal system. So let us moving in this way. How can we solve this problem, that is the direction of choosing of a plane in the crystal system? So what are the direction of in the unit cell, that is space lattice, or is this direction is unique, that is for a given space lattice you have only single direction? Is it possible? So direction of a line is associated with certain indices to the line. So you have not keep all the points or the direction points in a fractional manner. In previous case I have given that is half, 1/3, half. This is not a proper representation of the direction of a line in the unit cell. So second point, if the line passes through the origin, you have to take the projection on 3 axes to get the direction. So if you want to get the direction, you have to take the projection on 3 axes. Now let us choose this as a unit cell. I extend this unit cell to a bit along this side. Now what is the direction, or how could you choose the specific direction in this unit cell? So let us consider ABC is basically the unit cell parameters, and obviously as I choose this a cubic system, so all angles are 90 degree. Now take this 3 direction, which obviously I have chosen as the 3 axis in my previous case. So the 3 direction must be, this is obviously 1 0 0 of the x-axis, this is obviously 0 1 0, this is obviously the y-axis, and this is 0 0 1, this is z-axis. Now what is the direction of this red line? As you see here, if we take the projection, it must passes through the origin. So the projection of this particular point on this plane is 1, on this plane is unit, and on the other plane, that is this plane, this is also unit. So the direction is 1 1 1. Now choose this line. So this line is passing through the origin, but what is the direction of this line? So this will be 1 bar 1 0. How this is 1 bar 1 or 0? Now as this line that passing through the origin, you cannot get any intercept on x-axis, so you have to given a shift of this line to get the intercept. On the other hand, this line intercept with z-axis at infinite, because this is parallel with z-axis, so the third coordinate will be 0. Now with intercept with b, if you drop a projection here on this b plane, this will be unit, so this will be 1. Now you have to make a shift. So the shift line either along this direction. So if you choose this direction, or this is the origin and this is the shifting, so the intercept with x-axis will be -1. So this will be 1 bar 1 0. And if any of this line, this two line parallel with this, must have the same direction, so this will be 1 bar 1 0. Now take this line. Now it is a homework for you, that what is ultimate direction of this line. Now come to the next part, that is orientation of lattice point. So you just see here, there is some dots, and these dots is nothing but a two-dimensional lattice point. Now my question is that, is the choice of these planes are unique? That means the plane which I suppose in crystal, they must contain some lattice points. So now first take this lattice point as a similar one and choose this red line as the family of planes or the parallel planes in the crystal system. Now some of you may not choose this as the family of planes. So one can choose this this blue line as the family of planes. Some other fellow, he can choose this green line as the family of planes. So the proposition is that this choice of family of planes is not unique, but there is a proposition that the choice is characterized by its direction. How? Because if you choose this as a family of plane, this family of plane must be characterized by a specific interplanar spacing. But when you choose this family of planes, the interplanar spacing may change. In case of this proposition, interplanar spacing may be changed, not maybe, it must be changed. Okay, so I have said here that the choice is characterized by its direction. Now what is that how could you choose this family of planes, or rather the direction? First, before the proper indices scheme, Weiss give the law of rational indices. How does it mean? Take this three coordinate axis. This is x-axis, this is y-axis, this is b-axis, and this point is the origin. Now choose this ABC as a plane. And what is the characteristics of this plane? That this plane is unit plane, because you take a unit A distance from origin to draw this point, you take B distance from the origin to move to the point B, and you take C distance to move this point C. So this ABC plane is basically unit plane, or the smallest possible plane for a coordinate system specified by this ABC units of cell length or unit of movement along three direction. Now you choose another set of plane, so another plane, that is PQR, and which have the following characteristics. What is the characteristics? Now say OP, that is equal to some m in times A, OQ some n times B, and OR some L times C. So you can say here that this plane is nothing but the expansion of this ABC plane by a fractional amount MA along x-axis, NB along y-axis, or LC along z-axis. Right? There is no problem with this proposition. Now, this N, M, and L are just the multiple factor, and this multiple factor must be some integer. So this law is called the rational indices, or this indices is known as wise indices. But this wise indices is good for this type of plane. Now what is the problem with this wise indices? You take this 3-axis xyz and this brown plane, right? So if you look at the system here, this brown plane never intercept with either x-axis or y-axis, but it intercept at a fractional amount L in times C along z-axis, or 1 times C along z-axis. Okay, so brown plane intercept on 3 axes with this proposition, that is infinite along y-axis, infinite along x-axis, or LC amount along z-axis. So according to this wise indices, the indices of this plane will be infinite L, but infinite indices is not defined, because you cannot define an infinite indices plane for a crystal system. So you have to come with Miller indices. What does it mean? You have to take the direction of a plane, but the direction never be infinite. It is always some integer. It never become a fraction. The plane never consider on the origin. You never consider a plane which passing through the origin for calculation of this Miller indices. And the last part, you have to choose the reciprocal of the intercept, and then what you do, the plane described in the crystal are noted by this Miller indices, and this is given by HKL. So after taking the reciprocal, you have to make this reciprocal to the nearest integer value, right? So these things you have to remember or keep in mind when you are going to calculate the Miller indices of a plane, right? So Miller indices ultimately gives the direction of some plane in the unit cell, and as according to proposition this never be infinite, so the problem of Wise law is removed. Now how it is removed? So how could you determine the Miller indices of a system? Now choose a specific plane that do not pass through origin. Take the intercept of the plane with 3 axes, right? Take the reciprocal of the intercept and make the reciprocal to the smallest integer value by multiplying some factor. So these are the rules of determination of Miller indices for a specific crystal system, right? So let us consider a plane that intersect with x-axis at one lattice parameter distance and y and z axis. This is parallel to y and z axis. As in the first case for brown plane, it will be 1 along L along z axis and infinite along x and y axis. So the Miller indices of that particular plane will be h reciprocal of 1, that is 1, reciprocal of infinite, that is 0, and reciprocal of infinite, that is 0. So hkl in that case written as 1 0 0. So in this way you can determine the Miller indices. Now this for this example I am coming here. For the first example, the plane intercept at a by 2, b and c. So how could you uh, calculate the Miller indices for this plane? So you have to take just the reciprocal of the intercept here and make it to a integer, nearest integer. In second case, it is twice a, b and 3c. You again take the reciprocal of this 3, then make it integer, just reciprocal this coefficient. Now for this case, as this is infinity, so 1 upon infinity this becomes 0. And for this case, again for a negative sign, it will be different. I am just going to calculate these things to in the next section. First, choose a cubic system. Now this is the plane for which you are going to calculate the Miller indices. Now definitely you choose the origin at this point. Is this choice correct? No, because the plane is passing through the origin. So the origin choice is not correct. Now what I should do? Choose this point as origin, this green circle. Now this origin never considered on plane. So this choice is wrong, but my next choice is correct. Right? Now what you should do? You just take this XYZ axis at the origin here and just expand this axis in the reverse direction. So if you expand in reverse direction, this will be minus x, this will be minus y, and this will be minus z. Now if you choose the origin here and you shift this whole coordinate system to here, you see that the intercept of this plane along z axis will be minus 1 and intercept of this plane along x axis, what is this? This will be, this is parallel to x axis, so this is infinite, and with y axis what is again with the y, if this is y axis, so this is again infinite. So what is the value of this Miller indices? This becomes intercept infinite infinite minus 1, so reciprocal is 0 0 minus 1, and obviously you cannot write this minus 1 in the Miller indices. You have to write 0 0 1 bar, so this is called bar. Okay, so the Miller indices of this plane is 0 0 1. Now I am going to calculate the Miller indices for above 3 examples. Now I am coming to the example of
the determination of Miller indices for 3 examples. My first example is a plane which intersects at this A by 2, B and C by 3, this intersect. Now, what is the coefficient of this 3 intersect? This is half, 1 and 1/3. So these are basically intercepts with 3 axes. Now you have to take the reciprocal. So reciprocal is 2, 1, 3 for first plane. So 2, 1, 3 is the Miller indices for the plane which intersected this fractional intercept. Now for second example, the plane which intercept at 2A, B, 3C point. Now the intercept is 2, 1 and 3. Now take the reciprocal value. This will be half, 1, 1/3. Now clear this fraction. So you have to take LCM of 2 and 3. So LCM of 2 and 3 is 6 and multiply this 3 term with 6. So Miller indices will be 6 into half, that is 3, 6 into 1, that is 6, 6 into 1/3, that is 2. So 3, 6, 2 is the Miller indices of this plane. Now come to the third example. So for third example, the plane is A, 3B, infinite. So the plane is parallel to z-axis, right? So it never intersects with z-axis. So the intercept are 1, 3, infinity. Now take the reciprocal. What is the value? 1, 1/3, 0. Now just remove this fraction. So LCM of 3 and 1 will be 3. So Miller indices will be 3, 1, 0. So this is Miller indices of this A3B infinite plane. Now come to the fourth example. Now the fourth example, the plane intercept at A minus twice B and 3C point. So you have to take the intercept. This will be 1 minus 2, 3. So reciprocal will be 1 minus half, 1/3. Now take Miller indices. By LCM of these two is 6. This is LCM. So Miller indices will be 6. Here it is 3 bar, this 2. This becomes minus 3, so this will be 3 bar. Right? So for this plane, Miller indices is 6, 3 bar, 2.
Now for cubic system, these are some example of planes. So if you choose this plane, the h scale will be 1 0 0, as you find here the intercept of this plane with 3 axes, and take it reciprocal and make it the nearest integer. Now the Miller indices of this plane will be 1 1 0, and obviously this plane is 1 1 1. Now you have to take these steps to get the Miller indices, as I mentioned earlier. Now the crystal plane can be negative, and it is represented by bar, as I mentioned here. Now there exists some family of planes. The family of planes means the equivalent planes which are basically make this geometric figure complete. So as I see here, for a cube there are 3 faces, which is represented by 1 0 0, 0 1 0, and 0 0 1. So the plane of which is represented by Miller indices, that is given within the first bracket, and obviously this family of plane, as this makes this geometric figure complete, is represented by the first plane 1 0 0 within 3 bracket. Okay, so this includes all 3 planes of a cube, and other combination which contains negative, obviously 1 bar. If you take 1 bar 0 0, take 0 1 bar 0, and you take 0 0 1 bar, that is also included in this family of planes of 1 0 0. Right? Now these are some equivalent planes or family of planes in the crystal system. This 1 0 0, 0 1 0, 0 0 1, these 3 are the family of planes. Again, 1 0 0, 1 1 0, 1 0 1, 0 1 1, and obviously they are negative signs. That means 1 1 bar 0, or 1 bar 1 bar 0, or 1 bar 0 1, or 1 0 1 bar, and 0 1 bar 1, 0 1 bar 1 bar, even 0 1 1 bar. These all are obviously some family of planes of these classes. Again, 1 1 1, 1 bar 1 1, and 1 1 1 bar, these are also the same family of planes. Now only this blue line, which is represented as the positive shift, and this red line represent the negative shift of this plane or the family of planes. Right? Now what is the problem with hexagonal system? Now as you see here, I have spent a very little bit time with hexagonal system, as this system is not included in your syllabus, but just read it, that hexagonal system have not equivalent with the cubical system, because hexagonal system have 6 faces, as I mentioned here. Those faces are 1 0 0, 0 1 0, 1 bar 1 0, 1 bar 0 0, and 0 1 bar 0, 1 1, 1 1 bar 0. Now sum of the plane is represented here, that is 0 1 0, 1 0 0, 1 1 bar 0, this plane. But the problem is that you have not make those 6 planes under same category, because here is 2 0, here is 2 1, here is also 2 1. So these 6 planes are not of same category. So you have to introduce another indices, that is given by I, and make this I equal to minus h plus k. Now sometimes this is written as hk dot l, means you can find I from the value of h and k. So this must be family of planes. Now what are the family of planes? So 6 hexagonal family of planes is in this way, and we have to choose the 4 axes to represent hexagonal system: a1, a2, a3, and obviously c. So 1 0 1 bar 0, 0 1 1 bar 0, 1 bar 1 0 0, 1 bar 0 1 1, 0 1 bar 1 0, 1 bar 1 1 bar 0 0, which are now belonging to this class of this family of planes. So 1 0 1 bar 0 is the family of planes for hexagonal system. So now how do you get the direction of a in a crystal system? So you just take a coordinate and make a vector which is running from the origin to that point, and you just take the coefficient of the smallest unit translation along any direction on the unit cell, and that coefficient within the third bracket represent the direction of that particular vector. So if you choose this direction, so this direction with, you have to join this point with the origin first, then you have to take the direction of this vector with UVW. Now it intercept with x-axis at 0, so the value of u is 0. Now with y-axis this is 1, so projection of this is 1, and projection of z-axis is 1, so this will be 1 1 0 direction. So the direction of family like 1 1 0, and this is also 1 0 1, this is also 0 1 1, these three are obviously the some family of planes. So 1 0 0, this 3 1 0 0 0 0 1 and 1 0 0 1 0, these are three family of planes. Again this green three planes also some family of planes. Again for crystal cubic system there are 1 1 1 family of planes. Sum of 1 1 family of planes is represent as the diagonal of this cube. So if you choose the diagonal of this cube, each diagonal falls under this family of planes. Okay, so these are the family of direction in the crystal system. So how could you equivalent or choose equivalent or same direction? Now you take 2 or 3 vector. One is just clean UVW, so it passes through UVW point. Now if another one choose 2U 2V 2W and half U half V half W, this 3 also equivalent with UVW plane, as you have to convert this fraction to the integer, or you have to reduce this integer to its lowest term, so you get the same plane or same direction in the crystal system. Now what is the crystal direction? So if you determine the direction, you have to identify the head and tail of the direction, and you convert this to the fraction or integer and reduce to the lowest term. So you have to make either fraction or make either integer to reduce the term, or to increase the value of it to the nearest integer and enclose that term within some bracket. You will get the direction. Now for hexagonal system, this is not under your syllabus, but I have to say that there are 4 indices for the direction u, v, t, w, and this direction is related by this vectors, translation vector u, v, w. So the family of planes 1 1 0, if you take 1 1 0 0 for hexagonal system, the same thing if you put here, this will gives you 1 2 1 bar 1 bar 0 and 2 1 0 this. Okay, now what is the relation between direction and the planes? So for a cubical system, planes and direction have same integers, but they are perpendicular to each other. Now if you choose that this 1 0 0, this green plane, and you take 1 0 0 direction, but you see here that this 1 0 0 direction means it intercept with this plane intercept with x-axis at unit fractional unit crystal parameter dimension, and it does not intercept with y and z axis at all. So you get 1 0 0 plane, and the direction of 1 0 0 is basically x-axis. So this 1 0 0 direction and 1 0 0 plane, they are perpendicular to each other. In the similar way, 0 1 0 direction and 0 1 0 plane obviously perpendicular, and the same thing happens for this direction. This 0 0 1 and 0 0 1, these two are obviously same direction. Now same thing happens for the diagonal plane also. So if you take this direction, so the direction will be perpendicular to this. If you take all these three direction of the side of this triangular plane, all direction will be perpendicular to 1 1 0 plane, right? So you will get the direction relation between direction and plane. So the same plane for a cubic system is perpendicular to its direction. So now I have to end this class, and in the next class I am going to discuss the next part of this crystal structure. Thank you.